So I said we were going to talk about other phenomenological forces in this video, but I lied. We're actually going to talk a little bit more about friction because I think that it's worth kind of working through an example of that because it's one of those things that people get really confused about. So there's a friction example, and it's actually an example that I think I've given you on the module exercises. So if you are watching this video, you can think about this problem pretty directly. So we've got a coffee cup. It's sitting on the table. Okay. And I want to think about what happens as far as frictional force when I sort of come along with my hand. So this is my hand here. Boy, I really need to take some art classes, huh? That's my God. That's a hand. And I start to push on the coffee cup. And I push lightly initially, but I push harder and harder and harder. So if I actually think about what the force is that I apply versus time, so this is the force of my finger versus time, right? At t equals 0, I just start to touch that coffee cup, and then as time goes on, I apply more and more force to the object. Okay, and the question is, what is the frictional force when I do that? Well, if I think about keyframes for this, one keyframe is when I first started pushing. I'm pushing not very hard at this point, right? And in fact, I'm pushing such that the force that I'm applying, so the force of my finger, is less than the static coefficient of friction times the normal force, right? So just to note this, there's a gravitational force that's acting on this coffee cup, m times g. Because there's a force down and the coffee cup's not falling into the table, there must be a normal force that's equal to plus, so this is minus mg j hat. There must be a force plus mg j hat that's the normal force, so the table is pushing up with a normal force. So long as the force that I'm applying with my finger is less than the static coefficient of friction times that normal force, the object doesn't move. Right, it's still in the static case. Okay, and so for that time, right, so if this is sort of up to some point in time that this is not true, then the frictional force, the magnitude of the frictional force, is actually just increasing to accommodate however much I'm pushing, right? So if I'm pushing with a force of 1/100th of a newton, the frictional force is also 1/100th of a newton in the opposite direction. When I push with 2/100ths of a newton, the frictional force is 2/100ths of a newton. So for that time, like if this is time 1, right? Up to time 1, the frictional force is increasing and is directly opposing the finger force, right? So I have my force of the finger here, and then there's also a frictional force that's acting and is equal and opposite, so the cup doesn't move. Okay. At some point, I actually apply enough force that, so case 1 is the frictional force, the finger force is less than mu sub s in 2. Point 2 in time, we'll say that my finger force is equal to mu sub s times n. Okay. And up until that point, this frictional force is increasing. Okay, so up to point 2, and at point 2, notice that the magnitude of the frictional force now is mu sub s times n. Okay. And it's still not moving, right? So we could also plot the velocity of the object versus time, and up till point 2, the velocity is 0. Okay. Now, once we start to push any harder than mu sub s times n, that's actually the point at which we start to break these bonds at the surface, and the object begins to move, right? So now, case 3, we're actually pushing with a force that's greater than mu sub s times n. And so the object begins to slide, so the object is moving, right? And so the object begins to accelerate, right? The velocity starts to increase at that point. And now, what's the case? Well, now we're moving the object across the surface. These bonds are breaking. The atoms are starting to shake as it's getting moved across the surface. And there is a frictional force that resists that motion, which is the kinetic coefficient of friction times the normal force, and that kinetic coefficient of friction actually doesn't care how hard I'm pushing so long as it's moving. So once I'm pushing any harder than that static coefficient of friction times the normal force, at that point the force of friction actually becomes constant at a value of mu sub k times n. Now I've drawn this actually as dropping at that point, and the reason for that is that typically mu sub s is usually greater than mu sub k. It's usually the case that the static coefficient of friction is bigger than the kinetic coefficient of friction. And ballpark, these numbers, it depends on what types of materials and what kinds of interfaces you're talking about, but this might be, say, 0.8, and this might be 0.5 or something like that, depending on the surfaces that you're interested in. Okay. So you have two regimes, right? One regime is this regime, where friction is acting as a constraint force. And the other regime is once you're moving, friction is just a constant of mu sub k times n.